Welcome, everyone. I want to talk to you about act locally, learn globally. It's a phrase we use internally a lot to combine IoT and data worlds into a single world. My name is Anoop Dawar. I run product management and product marketing at MapR Technologies. Let's start with just a quick overview of what MapR does. So MapR has built a platform for all data across every cloud, um, and it allows you to essentially ingest, store, manage, analyze, process, and then apply the insights from the data in real time to your business processes. And the way we do it is we want to allow the embracing of the existing and legacy applications with new generation applications, whether they are pure analytical applications or even real-time operational applications. So let's talk about IoT a little bit, right? In the Internet of Things is all things to all people. There are a lot of ways people think about it. But if you look at all the way from the chips that are in the sensors to the edge devices, to then how the data streams from these systems into the network and back to the cloud, it's actually a whole data fabric. It's a massive billions of events, billions of devices data fabric. And in order to be able to harness the energy of that data fabric and take actions, you need to be able to learn from everywhere, learn from every edge device, every IoT system, and then act anywhere at any time. So you need to be able to then have that global knowledge and then be able to quickly spread that global knowledge to the edge devices so that the edge devices can then take local actions, even in cases where it's unable to connect to the mothership. So you're in systems and locations which are occasionally connected and occasionally disconnected. So let's take an example. I think we've all seen how connected cars and autonomous car revolution is going to take big strides in the next few years. But if you then look at the amount of data these systems generate, it's completely mind-boggling. So for example, in pre-production, a car generates 50 terabytes of data an hour. Imagine how much data that is, right? And so if you then try to expand it, even if you compress it, you will get literally a petabyte of data from every car every year. How do you deal with that complexity? When you look at these use cases that people want to power with autonomous systems, you will see uh, use cases that are very advanced, driver assistance use cases like helping with lane change, traffic sign recognition, pedestrian recognition, entity recognition, to computer-aided driving, the ability to detect traffic jams and road conditions and weather conditions, to just basic vehicle maintenance and healthcare, and then finally radically understand and figure out how will the insurance models and the economic models for these autonomous systems work. Um, so I'll give you an example of a customer of MapR that's actually trying to do pre-production autonomous vehicles and looking to how bring it into production. So here is a classical pre-production connected vehicle. Thousands of tests are running on a sample of pre-production cars 24 hours a day. Because they have a few pre-production pilots, each pre-production pilot costs a lot of money, they run these cars in 3 shifts of 8 hours each. After every 8-hour shift, the car docks in, the disk drives are removed from the car, and new disk drives are put in the car, and then it goes for another 8-hour shift. So you're literally getting now 8 to 10 to 20 terabytes of data every 8-hour shift from each car getting into the MapR system. But usually, it takes you then 24 hours to bring it into a quote-unquote data center where you can then analyze every signal that happened, every event that happened, and then figure out what you can do to your software and your machine learning models to improve your next run of that autonomous vehicle or a connected car, which is simply too long. So what they did is they brought an edge system inside MapR, inside the car, which is sitting in a trunk. Imagine, for those of you who remember the days of 6 CD players that were in the trunk of your car, think about that form factor of an intelligent device that's sitting in the trunk of your car and can, basically consume terabytes and terabytes of data, but also have a machine learning model in there that can be tweaked for the real-time conditions and act immediately. And that shrinks the time to insight fairly quickly. And you can then iterate over the conditions of your environment, and the more iterations you can do and the faster iterations you can do based on the environment, the quicker your system is going to become more autonomous and learn better. So this is sort of the architecture or the framework or how this system gets built. It has these systems at the edge. The edge could be any edge. It could be an autonomous vehicle. It could be a hospital. It could be an oil rig, where you have a point of presence, a complete system that stores reliably, has a full analytical stack and a full operational stack so that it can do machine learning and then have machine learning models that are changing on the fly and act while also simultaneously sending only the relevant information to your central data centers so that the central data centers can still continue to learn globally. So you have a point of presence on your edge, could be millions of devices or billions of devices, and then you have a point of presence in your core data center or your public cloud where you're learning globally. This is what we call the act locally, learn globally architecture. To summarize, we call it the ability to leverage local data from numerous sources for constructing ML and deep learning models with global knowledge. And then these models can be rapidly deployed at the edge to enable real-time decision making. So there is a streaming framework that's built into the system that allows you to push machine learning models either from the cloud to the edge or from the edge to the cloud, so you can deploy them in real time. Let's look at a couple of more examples, but before I go into that, I wanted to show you how small this edge deployment could be. So for those of you who are familiar with Intel NUC machines, and if you haven't seen one, you go to our booth on aisle 400 and you'll see 3 Intel NUCs that are running most of our demos. There are about 5 demos in the booth that are running on Intel NUC machines. And these are really small form factor machines that can be placed in any location and can give you a full, complete data stack. So let's look at another example. So this is an example of an oil company that has thousands of oil and gas sources. And the interesting thing we found out is whenever they would have a contractor that was going to the oil rig to service any equipment, they would send a laptop with that contractor. The contractor will take that laptop, plug it to various devices, download the information that they needed, and then bring it back to a place where they could then connect it to their global data center. And then that's how they were getting all the information of all their oil rigs, which takes, as you can imagine, a lot of time and effort and cost. Once that data is inside their data center, then they can analyze and figure out and do analytics on it. So again, by simply installing an edge on the oil rig, they were able to sort of consolidate all that data into a single system. And then whenever there is connectivity, let's say a contractor comes in with a Wi-Fi signal or a 3G signal, the edge device just connects to the network and ships the data as required, compressed, secure, and only the data that you require to be shipped and not all the data. And you can basically, again, reduce the time to insight from hours, from a couple of days to about 2 hours. Another example is a medical device company. So this is, again, another interesting way to look at how IoT can change the world. If you imagine even simple things like MRI scans, any of you who've ever been to get an MRI scan or has had a family member or relative get an MRI scan, you know that after the scan, it takes a while before the results come to you. And the reason is the systems have to do very complex image processing and algorithms to figure out and give you a report. And those things typically take time. But the interesting insight is that the data that's generated from the scan is fairly small. It's not that huge. So if I can take that data across all the machines in a hospital and immediately, let's say, ship it to a cloud where I have infinite compute resources, I can quickly do the MRI scan in a matter of minutes instead of taking hours or days. So while the patient is sitting in the hospital after finishing their scan, the scan is being analyzed in the cloud immediately. The results, again, are fairly small. They can get pushed back to the edge, and you can have a conversation with your doctor within minutes of having an MRI scan, and it just shrinks the amount of pain that all of us as patients go through with these kinds of situations. So just to briefly summarize, what this system does is that you can now enable a way to reduce bandwidth requirements from the edge to the cloud, because if you try to ship all the data from all the edge to the cloud, it's going to be nearly impossible to do. because the amount of data on the edge systems is going to be 50% of the total data in the world, or maybe even more. And we just simply, as a nation or world, don't have that kind of a capacity. So you need to be able to shrink that data, maintain data privacy, do the analysis, anonymization, authentication, and the compression and security encryption before you ship the data, comply with all the standards, bring it back if required, and also deal with the sometimes connected, sometimes disconnected world with IoT machines. Because IoT it's not like just a phone in our pockets, which is almost always connected. It could be a remote oil rig, it could be a hospital in a remote location, it could be an autonomous vehicle that just happens to get crashed and has its communication system broken down. Um, and it needs to be able to address everything globally, because if I want to act locally from global knowledge, the global system needs to be able to find you and push that information and knowledge to you, and vice versa, the local system needs to know how to talk to the global system. And so what you get is you basically get a small platform in a box, which gives you full analytics with Spark, with machine learning, with SQL capabilities, with a database, but also a reliable storage engine that can store with reliability, enterprise-grade reliability, the data you have, and then ship it on demand or in real time to your global system. That's the talk for me for today. If you have any more questions, I'm happy to wait, and you can also check out our booth, which has 5 demos, including one of the a racing car demo that showcases this technology on an Intel Nook. Thank you very much.